Hi, welcome back to educator.com. Today we're going to talk about properties of functions. Functions are extremely important to math. We keep talking about them because we're going to use them a lot and they're really useful. To help us investigate and describe the behaviors of functions, we can talk about the properties that a function has. So there are a wide variety of various properties that a function can or cannot have. This lesson is going to go over some of the most important ones. While there are many possible properties out there that we won't be talking about in this lesson is still going to give us a great start for being able to describe functions, being able to talk about how they behave, how they work. So this is going to give us the foundation for being able to talk about other functions in a more rigorous way where we can describe exactly what they're doing and really understand what's going on. Great. All right, first one, increasing, decreasing, constant. Over an interval of x values, a given function can be increasing, decreasing, or constant. That is, always going up, always going down, or not changing. Its number will always be increasing, its number will always be decreasing, or its number will be not changing. And by number I mean to say the output from the inputs as we move through those x values. This is really much easier to understand visually, so let's look at it that way. So let's consider a function whose graph is this one right here. So this function is increasing on -3 to -1. So we've got -3 to -1 because from -3 to -1, it's going up, but it stops right around here. So it stops increasing on -3. It stops increasing after -1, but from -3 to -1, we see it's increasing. It's probably increasing before -3, but since all we've been given is this specific viewing window to look through, all we can be guaranteed is from -3 to -1, it is increasing. Then it's constant on -1 to 1, right? It doesn't change. As we go from -1 to 1, it stays the exact same, so it's constant on -1 to 1. However, it is increasing before -1, and it is decreasing after 1. So decreasing on 1 to 3, because we are now going down. So it continues to go down. So from 1 on to 3, because we can only be guaranteed up until 3. It might do something right after the edge of the viewing window, so we can only be sure of what's there. So it is decreasing from 1 to 3. Great. So that's what we're seeing visually. It's either going up, straight, or down. It's either horizontal, it's going up, or it's down. Increasing means going up. Constant means flat. Decreasing means down. Formally, we say a function is increasing on an interval if for any a, b in the interval where a is less than b, then f of a is less than f of b. Now, that seems kind of confusing, so let's see it in a sort of picture version. So let's say we have an interval a to b, and this graph is above it, right? So if we've got some interval, so it's any interval, so let's just say we have some interval, right? That's what is between those two bars. And then we decide to grab two random points. We choose here is A and here is B, right? So A is less than B, so that means A is always on the left side. So A is on left because A is less than B. That's not to say B over C, that's because. I'll just rewrite that. I might get that confused in math. So A is on left because A is less than B. So if we then look at what they evaluate to, this is the height at f at A, and then this is the height at f at B. And notice f of B is above f of A. F of B is greater than f of A. So it's saying that any point on the left is going to wind up being lower than points on the right in the interval when it's increasing. So in other words, the graph is going up in the interval as we read from left to right. Remember, we always read graphs from left to right. So during the interval, we're going from left to right. We're going up as we go from left to right. We have a similar thing for decreasing. We've got some interval, some chunk interval, and we pull up, we've got some decreasing graph. Right? And if we pull up 2 points, A, B, so A has to be on the left, B, because we've got A is less than B, then f of A is greater than f of B, right? F of A is greater than f of B. So decreasing means we're going down. The graph is going down from left to right. So we don't want to get too caught up in this, this formal idea. We're just some interval, there's some place where if we were to pull out any 2 points, the one on the left will either be below it, if it is below the one on the right, if it's increasing, and if it's decreasing, it will be above the one on the right. We don't want to get too caught up in this. We more want to think in terms of going up, going down in terms of reading from left to right. Finally, constant. If we've got some interval, then within that interval, our function is nice and flat, because if we choose any a and b, hey look, they wind up being at the exact same height. So there's no difference. F of a is equal to f of b. The graph's height does not change in that interval. While the definitions on the previous slide give us formal definitions, they give us something that we can really sink our teeth into and understand if we want to talk really analytically, we don't really need to talk analytically that often in this course. It's going to be easiest to find these intervals by analyzing the graph of the function. We just look at the graph and say, well, when is it going up, when is it going down, and when is it flat? That's how we'll figure out our intervals. We won't necessarily be able to find precise intervals, right? Since we're looking at a graph, we might be off by a decimal place or two. But for the most part, we're going to be pretty darn close, so we can get a really good idea of what these things are, what these intervals of increasing, decreasing, or constant are. So we get a pretty good approximation by looking at a graph. And if you go on to study calculus, one of the things you'll learn is how to find increasing, decreasing, constant intervals precisely. That's one of the major fields, one of the major uses of calculus. You won't even need to look at a graph. You'll be able to do it all from just knowing what the function is. Knowing the function, you'll be able to turn that into figuring out when is it increasing, when is it decreasing, and when is it flat. You'll even be able to know how fast it's increasing and how fast it's decreasing. So pretty cool stuff in calculus. All right. Intervals show x values. For our intervals of increasing, decreasing, constant, remember, we're giving intervals in terms of the x values. It is not the points. We describe the function's behavior by saying how it acts between two horizontal locations. So we're saying between, -5 and -3 horizontally. It's not the point -5, -3. It's between the locations -5 and -3. And don't forget, we always read from left to right. So it's reading from left to right as we read from -5 up until -3. So the other thing is we need to be able to do it, we need to always put it in parentheses. So parentheses is how we always talk about increasing, decreasing, constant intervals. Why do we use parentheses instead of brackets? Well, think about this. A bracket indicates that we're keeping that point, right? A parenthesis indicates that we're dropping that point, not including that in the interval. But the places where we change over, the very end of an interval, is where we're flipping from either increasing to decreasing or increasing to constant. We're changing from one type of interval to another. So those endpoints are going to be changes. They're going to be places where we are changing from one type of interval to another, so we can't actually include them because they're switchover points. So we want to only have the things that are actually doing what we're talking about. The switchovers will be switching into something new, so we wind up using parentheses. All right, so real quick example, if we've got f of x equals x squared minus 2x, that graph on the left, then we see that it is decreasing until it bottoms out here. Where does it bottom out? It bottoms out at 1, horizontal location 1, and it is decreasing all the way from -infinity out until it bottoms out at 1. And then it is increasing after that 1. It just keeps increasing forever and ever and ever, so it will continue to increase out until infinity. So parenthesis, -infinity to 1, decreasing, and increasing, parentheses, 1 to infinity. We don't actually include the 1 because it's a switchover. At that very instant of the 1, what is it? Is it increasing? Is it decreasing? It's flat, technically, but we can't really talk about that yet until we've talked about calculus. So for now, we're just not going to talk about those switchovers. All right, next idea. Maximums and minimums. Sometimes we want to talk about the maximum or minimum of a function, the place where a function attains its highest or lowest value. We call C a maximum if for all of the x, all the possible x that can go into the function, f of x is less than or equal to f of c. So that is to say, c, when we plug in c, it's always going to be bigger than everything else that can come out of that function, or at the very least equal to everything else that can come out of that function. A minimum is the flip of that idea. A minimum is f of c is going to be smaller or equal to everything else that can be coming out of that function. So a maximum is the highest location a function can attain, and a minimum is the lowest function the lowest location a function can attain. On this graph, the function achieves its maximum at x equals -2. Notice it has no minimum. So if we go to -2 and we bring this up, hey, look, the highest point it manages to hit is right here at -2. Why does it not have a minimum? Well, if we were to say any point was its minimum, well, look, there's another point that goes below it. So since every point has some point that's even farther below it, there is no actual minimum because the minimum has to be lower than everything else. There is a maximum because from this height of 3, we never managed to get any higher than 3, so we have achieved a maximum, and that occurs at x equals -2. Great. We can also talk about something else. So first, let's consider this graph, this monster of a function, -x⁴ plus 2x cubed plus 5x squared minus 5x. So technically, this function only has one maximum, right? You can only have one maximum, and it's going to be here because it's the highest point it manages to achieve. It'd be at x equals 2. But it actually has no minimum. Why does it not have any minimum? Well, it kind of looks like this is a low point, but over here, we managed to get even lower. Over here, we managed to get even lower. And because it's just going to keep dropping off to the sides forever and ever and ever, we're going to wind up having no minimums whatsoever in this function because it can always go lower. There's no lowest point it hits. It always keeps digging farther down. But nonetheless, even though there's technically only one maximum and no minimums at all, we can look at this and go, well, yeah, but even if that's true that there aren't anything else, this point here, kind of interesting, and this point here, kind of interesting, in that they are high locations and low locations for that area, right? This is the idea of the relative minimum and maximum. We call such places, these places, the highest or lowest location. I'll switch colors, so blue, oh my, with yellow it's managed to. So blue here, green here. So a relative minimum are the ones in green, and relative maximums are the one in blue. And sometimes the word local is also used instead. So you might hear somebody flip between relative or local or relative. These places are not necessarily a max or a min for the entire function, for every single place, but they are such a maximum or minimum in their neighborhood. There's some little place around them where they are sort of king of the, king of their hill. So this guy is the maximum in this interval, and this guy is the minimum in this interval, and this guy is the maximum in this interval. But if we were to look at a different interval, there'd be no max or minimum in this interval because it just keeps going down and down and down. And if we were to look at even in here, it's like, well, clearly right next to them. If we were to really put a neighborhood around him, he'd keep going down. He's not the shortest guy around. He's not the highest guy around. But these places are the highest or lowest in their place. Okay, so this gives us the idea of a relative maximum, relative minimum. Formally, a location C on the x-axis is a relative maximum if there is some interval, some little place around that, some ball around that, that will contain C such that for all x in that interval, f of x is less than or equal to f of c. In its neighborhood, C is the highest guy around. It is greater than all of the other guys. Similarly, for a relative minimum, there is some interval such that f of x is going to be less than or equal to f of c, right? So in its neighborhood, it is the lowest guy around. So lowest guy around makes you a minimum, highest guy around makes you a maximum. That is to say, a relative maximum or a relative minimum. So once again, this is sort of like what we talked about before with the previous formal definition for maximum, minimum, and also for the formal definition of intervals of increasing, decreasing constant. Don't get too caught up on what this definition means precisely. The important thing is we've got this graphical picture in our mind of relative maximum just means the high point in that area, and relative minimum just means the low point in that area. That's enough for us to really understand what's going on here. Getting caught up in these precise things, that's really something for like a late high-level college course to really get worried about. For now, it's enough to just get an idea of, oh, it's the high place, or oh, it's the low place. Don't forget, the terms relative and the terms local mean basically the same thing. Actually, they mean exactly the same thing. They can be used totally interchangeably, and some people prefer to use one, some people prefer to use another, some people will flip between the two, so don't get confused if you hear one or you hear another one. They just mean the same thing. To distinguish relative local maximums and minimums from a maximum minimum over the entire function, we can use the terms absolute or global to denote the latter. So if we want to say it's the maximum over the entire function, we could call it the absolute maximum or the global maximum. So a absolute global max min is where the function is highest, lowest over the entire function, which is exactly how we defined max min at first before we started to talk about the idea of relative max and relative min. So absolute global max min is over the entire function. The function highest, lowest over everywhere in the domain. Oops, everywhere. If we want to talk about all the relative or absolute max min function, we can call them the extrema or the extrema. Why? Because they're the function's extreme values. They're the extreme high points and the extreme low points that the function manages to go through. So we can call them the extrema. So there we are. There's just something for us, extrema, extrema. If we want to talk about relative absolute max mins in general, we use this word to do it. And absolute global talks about the single highest or single lowest. Relative just talks about one that is high or low in its neighborhood, in the area around that point. Just like finding increasing, decreasing, constant intervals, we want to do this from the graph. We don't want to really get too worried or too caught up on these very specific definitions, the formal definitions we were talking about on the previous slide. We just want to go, okay, yeah, we see that's a high point on the graph, that's a low point on the graph. So find your minimums, find your maximums by looking at the graph. And once again, if you go on to study calculus, you will learn how to find extrema precisely without even needing to look at a graph. You'll be able to find them exactly. You won't have to be doing approximations because you're looking at a graph, and you won't even have to look at a graph to find them. So once again, calculus, pretty cool stuff. Average rate of change. So this is also can be called average slope. When we talked about slope in the introductory lessons, we discussed how it can be interpreted as the rate of change, how fast up or down the line is moving, right? If we've got a line like this, it's not moving very fast up. But if we've got another line like this, it's moving pretty quickly up. So it is a rate of change. The slope is how fast it's changing, the rate of change. How fast are we going up? Now, most of the functions we're going to work with aren't lines, but we can still use this idea. We can discuss a function's average rate of change between 2 points. So if an imaginary line is drawn between 2 points on a graph, its slope is the average rate of change. So say we take 2 points, this point here, and we draw an imaginary line between them. Then the slope of that imaginary line is the average rate of change, because what it took to get from this point to the second point is we had to travel along this way. And while we actually went through this curve here, right, we actually went through this curve, but on the whole, what we managed to do on average is we really just kind of plunked along on that line. We could forget about everything we went through and we could just ask, well, what's the average thing that happened between those 2 points? And that would be our average rate of change. What was how fast were we moving up from our first point to our second point? So if we want to find the average rate of change, how do we do this? So let's say we've got two locations, x1 and x2. Now, we want to find the slope of that imaginary line between those 2 points on the function graph. So that line is sometimes called the secant line. For the most part, you probably won't hear that word too often, but in case it comes up, you know it now. Remember, slope, if we want to find what the slope of this imaginary line is, the slope of this secant line, we want to know, well, what is slope? How do we find slope? Remember, slope is the rise over the run. So it's the difference between our heights, y2 and y1, our second height and our first height. What did our height change by? And what did our horizontal location change by? Our second location minus our first location. So our horizontal distance is x2 minus x1. And our vertical distance is y2 minus y1. So y1 is the height over here, y2 is the height over here. So y2 minus y1 over x2 minus x1 is the rise divided by the run. Great. But what are y1 and y2, right? If we want to figure out what y1 and y2 are, well, we just need to look at what's x1 and x2, right? So since x1 and x2 are coming to get placed by the function, then y2's height is really just f of x2, because that's how the graph gets built. The input gets dropped to an output. We map an input to an output. And y1 over here is from f of x1. So since our original slope formula is y2 minus y1 over x2 minus x1, and we know that y1 is the same thing as f of x1 and y2 is the same thing as f of x2, we can just plug those in and we get the change in our function outputs, f of x2 minus f of x1, divided by our horizontal distance, x2 minus x1. Our average rate of change, we just look at how much did our function change by between those horizontal locations, how much did its output change by, divided by how much our distance changed by. It's often really useful and important to find what inputs cause a function to output 0. So if we've got some function f, we might want to know what can we put into f that will spit out 0. That is the values of x such that f of x equals 0. Graphically, since f of x, remember f of x is always the vertical component. The outputs come to the vertical. So if our outputs are coming from the vertical, then 0 is going to be the x-axis, right? We have a height of 0 here. So graphically, we see this as where the function crosses the x-axis. Our crossing of the x-axis is where f of x equals 0. This idea of f of x equals 0 is so important, it's going to go by a bunch of different names. It can be called the zeros of a function, it can be called the roots of a function, and it can be called the x-intercepts. So x-intercepts, that makes sense because it's where it crosses the x-axis. Zeros make sense because it's where we've got the 0 showing up. But how can we remember roots? Why is roots coming out? Well, one way to think about it, and actually kind of where this word's origin is coming from, is because it's the roots that the function is planted in, right? The function we can think of as being planted in the ground, not literally ground, but we can think of it as the ground of the x-axis. So it's like the function has put down roots in the soil. It's, not exactly perfect, but that's one good mnemonic to help us remember. Roots means where we are stuck in the soil. It's where we're stuck in the x-axis. It's where we have f of x equal to 0, or where we have an equation equal to 0. But all of these things, 0, roots, x-intercepts, they all mean the same thing. They're the x such that f of x equals 0. We can also use these for equations. We might hear it as the zeros of an equation, the roots of an equation, the x-intercepts of an equation. Great. There's no one way to find zeros for all functions. So we are going to learn, for some functions, foolproof formulas to find zeros, to tell us if there's zeros and what those zeros are. But for other functions, it can be very difficult, very, very difficult, in fact, to find the zeros. And although we're going to learn some techniques to help us on the harder ones, there are some that we won't even see in this course because they're so hard to figure out. But right now, the important thing isn't being able to find them, but just knowing that when we say zeros, roots, x-intercepts of a function or an equation, we're just talking about where f of x equals 0. So don't get too caught up right now in being able to figure out how to get those x values such that f of x equals 0. We really want to focus on the fact that when we say zeros, roots, x-intercepts, all of these equivalent terms, we're just saying where is the function equal to 0? What are the places that will output 0? Even functions. This is a slightly odd idea. That was a joke on accident. So even functions, some functions behave the same whether you look left or right of the y-axis. So for example, let's consider f of x equals x squared. It's symmetric around the y-axis. What do I mean by this? Well, if we plug in f of negative 3, that's going to wind up being negative 3 squared, so we get 9. But we could also plug in the opposite version to negative 3, right? If we flip to the positive side, negative 3 flips to positive 3. If we plugged in positive 3, then f of 3 is 3 squared, so we get 9 as well. So it turns out that plugging in the negative version of a number or the positive version of a number, negative 3, 3, we wind up getting the same thing. Negative 2 and 2 wind up getting the same thing. Negative 47 and 47 wind up getting the same thing. So whatever we plug in, as long as they are exact opposites horizontally, they are the same distance from the y-axis, the points are symmetric around the y-axis, they're going to come out to the same height. They're going to have the same output. We call this property even. And I want to point out it's totally different from being an even number. So it's different from even number, not the same thing as that. But we call this property even for a function because, well, sorry, not because. A function that is even is if all of the x in its domain, for any x that we plug in, if we plug in the negative x, that's the same thing as the positive x. Plugging in f of negative x is equal to plugging in f of x, right? So we plug in negative x into the function, we get the same thing as if we'd plugged in positive x, right? We can flip the signs and it won't matter as long as it's just negative versus positive. Why do we call it even? It has something to do with the fact that all polynomials, where all of the exponents wind up being even exponents, they wind up exhibiting this property, but then this property can be used on other things. So don't worry too much about where the name is coming from, but just know what the property is. F of negative x equals f of positive x. Right. Odd functions, the reverse of this idea. So other functions will behave in the exact reverse. The left side is the exact opposite of the right side. So for example, f of x equals x cubed behaves like this. If we plug in negative 3, then we get negative 3 cubed, so we get negative 27. But if we'd plugged in positive 3, we'd get positive 3 cubed, so we get positive 27. So you see, you plug in the negative, you plug in the negative version of a number, and you plug in the positive version of a number, and you're going to get totally opposite answers. However, they're only flipped by sign. Negative 27 and 27 are still somewhat related. They're very different from one another. They're opposites in a way, but we can also think of them as being perfect opposites. Negative 27's opposite is positive 27. So an odd function is one that behaves like this everywhere. We call this property odd. Totally different, once again, from being an odd number. A function is odd if for all x in its domain, f of negative x is equal to negative f of x. And that's a little confusing to read, but what that means is if we plug in negative x, then that's going to give us the negative version of if we'd plugged in positive x, right? So if we plug in negative number, then we plug in positive number, the outputs that come out of them will be positive, negative opposites, right? One of them will be positive, the other one will be negative. So negative on one side, positive on one side means that the outputs will also be negative on one side, positive on the other side. It's not necessarily going to be the case that the negative side will always put out negative outputs, but it will be the case that it will be flipped if it's odd. And this will make a little more sense when we look at some examples. And once again, why are we calling it odd? Once again, don't worry too much about it, but it's because it's connected to polynomials where all of the exponents are odd numbers, but don't really worry about it. Just know what the property is. Even odd functions and graphs. So we can see these properties in the graphs of functions. An even function is symmetric around the y-axis. It mirrors left-right, because when we plug in a positive number and we plug in a negative number, as long as they're the same number, they wind up getting put to the same location. They get output to the same place. An odd function, on the other hand, is symmetric around the origin, which means we mirror left, right, and up, down. Because when we plug in the positive version of a number, it gets flipped to the negative side, but also shows up on the opposite side. It flips to the negative height, or the positive height. Flips to positive, negative in terms of height. So let's look at some examples visually that'll help clear this up. So an even one, f of negative x equals f of positive x. So let's see how this shows up. If we plug in 0.5, we get here. If we plug in negative 0.5, we get here. And hey, look, well, beyond the fact that I'm not perfect at drawing, they came out to be the same height. If we plug in 2.0, and we plug in negative 2.0, they came out to be the same height, right? So you plug in the negative number and the positive number, and they wind up coming out to be the same height. That's what it means to be even. And since all the positives will be the same as the negatives, we wind up getting this nice symmetry across the y-axis. It's just a perfect flip. If we took the two halves and folded them up onto each other, they'd be exact perfect matches. It's just mirroring the two sides. Odd is sort of the reverse of this. F of negative x equals negative f of x. So, for example, let's plug in negative 1. So we plug in negative 1, and it winds up being at this height, just a little under 2. So let's see what happens when we plug in positive 1. If we plug in positive 1, it winds up being just a little under negative 2. So we flip the horizontal location. That causes our vertical location to flip. Let's try another one. We plug in 2.0. And we're practically past it, so we should be just a little bit before 2.0. And we plug in negative 2.0. Once again, just a little past it, so we're just a little before negative 2.0. And look, we wind up being at the same height. They're both, well, sorry, the same distance from the x-axis, but totally opposite directions, right? 2.0, positive 2.0, causes us to go to positive 4 in terms of height. But negative 2.0 causes us to go to negative 4 in terms of height. So they're going to flip. If you flip horizontally, you also flip vertically. And that's why we mirror left, right, and mirror up, down. So we are not just flipping around the y-axis. We're flipping around the origin because we're flipping the right, left, and the up, down. Flipping around the origin. Flipping the right, left, and the up, down. So we mirror left, right, we mirror up, down. That's what's happening with an odd function. All right, finally ready for some examples. Bunch of different properties that we covered now. Let's see them in use. First example, using this graph, estimate the intervals where f is increasing and decreasing. Find the locations of any extrema, relative max min, and our function is negative 1.5 x to the fourth plus x cubed plus 4x squared plus 3. Now, that's just so we can have an idea of, oh, that's what that function looks like. But we're not really going to use this thing right here. It's not really going to be that helpful for us figuring it out. So first, let's figure out intervals where f is increasing, decreasing. So first off, it is increasing from all the way down, and it sounds like we can probably trust that it's going to keep going down because we've got negative 1.5 x to the fourth. So it is increasing up until, looks like just after negative 1.0. So increasing from negative infinity, because it's going all the way to the left, it's going up as long as we're coming from negative infinity, because it goes down as we go to the left, but we read from left to right. So it's increasing from negative infinity up until, let's say that's negative 0.9, because it's just after negative 1.0. And then it's also going to be increasing from here. I'd say it starts there up until about this point. So where's that? Probably about 1.4. So increasing from 0 up until 1.4. Where is it decreasing? It's decreasing from this point until this point. So that was negative 0.9 we said before. So we'll go from negative 0.9 up until 0. And then it increased up until 1.4. So now it's going to be decreasing from 1.4. And it looks like it's going to just keep going down forever, and it does indeed. So it's going to be all the way out until infinity. It's going to continue decreasing. Great. Now let's take a look at the extrema, where are the relative max min. So we've got relative max min at all of these flipovers that we talked about, here, here, and here. So our relative max min, our high location, the absolute max min, in fact, is going to be up here. So relative maximums, we've got x equals, we said that was 1.4. So, and that point is going to be 1.4. Let's take a look according to this, and it looks like it's just a little bit under 8. So probably just a little bit under 8, let's say 7.9. And then the other one, the lesser of them, but still a relative maximum, it's occurring at x equals negative 0.9. So its point would be negative 0.9. And we look on the graph, and it looks like it's somewhere between 4 and 5. So somewhere between 4 and 5 looks a hair closer to 5, so let's say 4.6. Great. Relative minimum, or low place. Well, we can be absolutely sure of what the x is there. It's pretty clear that that's x equals 0. And what is the height that it's at right there? Looks like it's smack dab on top of the 3, so it's 0, 3. So we've got all of the intervals of increasing and decreasing, and we've also got all of our extrema, all of our relative maximums and minimums. Great. Example 2, a ball is thrown up in the air and its position in meters is described by location of t, distance of t is equal to negative 4.9 t squared plus 10t, where t is in seconds. Okay, so we've got some function that describes the height of the ball, where the ball is. What is the ball's average velocity, speed between 0 seconds and 1 second, between 0 and 0.01 seconds, and between 0 and 2.041 seconds? Okay, so first we've got some idea. Well, if we were to figure out what this function looks like, it's a parabola. It's got a negative here, so it's ultimately going to go down. And it's got the 10t here. If we were to graph it, it would look something like this. And that makes a lot of sense, because if we throw a ball up with time, the ball's going to go up and then come back down. So that seems pretty darn reasonable. So a ball's thrown up in the air and its position is given by this. But how does speed connect to position? Well, we think, what's the definition of speed? We don't exactly know what velocity is necessarily. Maybe we haven't taken a physics course. But we probably know what speed is from before in various things. So speed is distance divided by time. So distance over time equals speed. So it seems pretty reasonable that velocity is going to be basically the same thing. Not exactly true if you've actually taken a physics course, but that's actually going to work on this problem. We're going to have a good idea of what's going on with that, saying that that is true. All right, so what's the ball's average velocity? So the average velocity is going to be the difference in its height divided by the time that it took to make that difference in height. So we're going to be looking for distance. So if we've got 2 times time t1 to time t2, it's going to be the location at time t2 minus the location at time t1 over the difference in the time, t2 minus t1. Oh, and hey, that makes a lot of sense. It's going to be connected probably to what we learned in this lesson. Since student logic, they normally try to give us problems that are going to be based off of what we just learned. So t2 minus t1, oh, this looks just like average rate of change. Average rate of change of something's position. Oh, that makes sense that how fast it's going is the rate of change that the thing is changing its location. The rate that you're changing your location is the velocity that you have. Perfect. Great. So let's figure out, we need to figure out what it is at 0 seconds, what it is at 1 second right off the bat. So location at 0 seconds, we plug that in, -4.9 times 0 squared plus 10 times 0. Hey, that's just 0, which makes a lot of sense. If we throw a ball up at the very beginning, it's going to be right at the height of the ground. Distance at time 1 is going to be -4.9 times 1 squared plus 10 times 1. So we get 5.1. So if we want to figure out what is its average velocity between 0 seconds and 1 second, then we've got d of 1 minus d of 0 over 1 minus 0 equals 5.1 minus 0 over 1, which equals 5.1. What's our units? Well, we had distance in meters, time in seconds. So meters divided by seconds, we get meters per second. That makes sense as a thing to measure velocity and speed in. All right, next let's look at between 0 and 0.1 seconds. So if we want to find 0.01 seconds, location at 0.01 equals -4.9 times 0.01 squared plus 10 times 0.01. Plug that into a calculator, and that's going to wind up coming out to be 0.09951. So let's just round that up to the much more reasonable to work with, 0.01. Okay, so it rounds approximately to 0.01. So let's see what is the average rate of change then. The average rate of change then between 0 and 0.01 seconds is going to be d of 0.01 minus d of 0 over 0.01 minus 0 equals, oh, whoops, sorry, my mistake. So 0.01 is not actually what it came out to be when we put it in the calculator. I misrounded that just now. It was 0.09951. So 0.0, if it's 0.09951, if we're going to round that to the much more reasonable to work with thing, we actually get approximately 0.1. So it's not 0.01, but 0.01 still on the bottom, but the top is going to wind up coming out to be 0.1 minus 0 divided by 0.01. Sorry about that. Important to be careful with your rounding. So that comes out to be 0.1 over 0.01, which it comes out to be 10 meters per second. And now, you probably haven't taken physics by this point, but if you had, you would actually know that -4.9t squared, the -4.9t squared, that's the thing that says the amount that gravity affects where its location is. The 10t is the amount that the starting velocity of the ball is. So the ball gets thrown up at 10 meters per second. So it makes sense that its average speed between 0 and 0.01, hardly any time to have changed its speed, is going to be just pretty much what its speed started at. So that 10 meters per second is actually showing up there. So there's a connection here between actually understanding what the physics going on is and the math that's connecting to it. All right, finally, between 0 and 2.041 seconds, so let's plug in d of 2.041 equals negative 4.9 2.041 squared plus 10 times 2.041. So that's going to come out to be negative 0.0018. So it seems pretty reasonable to just round that to a simple 0. Now, what does that mean? That means at the moment, 2.041 seconds, that's when the ball hits the ground. It goes up at 0, and then it comes back down, and at 2.041 seconds after having been thrown up, it hits the ground precisely at 2.041 seconds. So 2.041 seconds, it's got a 0 height. So what is its average velocity between 0 and 2.041 seconds? So location at 2.041 minus location at 0 divided by 2.041 minus 0 equals 0 minus 0 over 2.041, which equals 0 meters per second, which makes sense. If we throw the ball up and then we look at the time when it hits the ground again, well, on average, since it went up and it went down, on average, it has had no velocity, because the amount of time that it has positive velocity going up and the amount of time that has negative velocity going down, it cancels itself out, because on average, between the time of it starting on the ground and ending on the ground, it didn't go anywhere. So on average, its velocity is 0 because it didn't make any change in its location. Great. Next example, example 3. Find the zeros of f of x equals 3 minus absolute value of x plus 3. So remember, zeros just means when f of x equals 0. So we can just plug in 0 equals 3 minus absolute value of x plus 3. So we've got absolute value of x plus 3 equals 3. We just add the absolute value of x plus 3 to both sides. So we've got absolute value of x plus 3 equals 3. That's what we want to know to figure out when the zeros are. When is this true? So remember, absolute value of x, absolute value of negative 2, is equal to 2, which is also equal to absolute value of positive 2. So absolute value of x plus 3, we know inside of it there could be a, since there's a 3 over here, we know inside of it there could be a 3, or there could be a negative 3. So inside of x plus 3, since it eventually, inside of that absolute value, because we know it's equal to 3, inside of that absolute value, we know that there has to be a 3 or there has to be a negative 3. We aren't sure which one, though, so we split it into two different worlds. We split it into the world where there is a positive on the inside, and we split it into the world where there is a negative on the inside. In the positive world, we know that not the absolute value, we know that what's inside, the x plus 3, is equal to a positive 3. In the negative world, we know that the x plus 3 is equal to a negative 3. Now, it could be either one of these. Either one of these would be true. Either one of these would produce a 0 for the function. So let's solve both of them. We subtract by 3 on both sides over here, we get x equals 0. We subtract by 3 on both sides over here, we get x equals negative 6. So the two answers for the roots are going to be negative 6 and 0. That's when the zeros of f of x show up. The zeros of f of x are going to be at x equals 0 and x equals negative 6. And if we plug either one of those into that function, we'll get 0 out of the function. Great. Final example, show that x to the 6th minus 4x squared plus 7 is even, show that negative x to the 5th plus 2x cubed minus x is odd, and show that x plus 2 is neither. All right, first thing we want to do is we want to remind ourselves, what does it mean to be even? So to be even means that when we plug in the negative version of a number, a negative x, it's the same thing as if we'd plugged in the positive x. Doesn't have any effect. And the odd version, actually, let's put it in a different color so we can see how all the problems match up to each other. So if we do with the odd version, then if we plug in the negative of a number, it comes out to be the negative of if we'd plugged in the positive version of the number. All right, so first one, show that x to the 6th minus 4x squared plus 7 is even. So that was really seeing that as expression as if it were a function. So let's show this by showing that if we plug in negative x, it's the same thing as we plug in positive x. So on the left, we'll plug in negative x. So negative x gets plugged in, becomes negative x to the sixth minus 4. Plug in negative x squared plus 7 equals, if we plugged in just plain x, we'd have plain x to the sixth minus 4 plain x squared plus 7. Great. So negative x to the sixth, remember, negative times negative cancels out to positive. We've got a 6 up here, right? We're raising it to the sixth power, so we've got an even number of negatives, right? Negative and negative, cancel. Negative and negative, cancel. Negative and negative, cancel. That's a total of 6 negatives. They all cancel each other out. So we've actually got negative x to the sixth, the same thing if we just said x to the sixth. Minus 4, same thing here. Negative x times negative x cancels and just becomes plain x squared plus 7 equals x to the sixth minus 4x squared plus 7. Turns out that it has no effect. If we plug in a negative x, it's the same thing as if we plugged in the positive x. Plugging in a negative version of a number is the same thing as plugging in the positive version of a number. So checks out, it is even. Great. Next one, let's look at odd. Negative x to the fifth plus 2x cubed minus x is odd. So we'll do this the same sort of thing. We'll plug negative x's in on the left side. So negative x to the fifth plus 2 negative x cubed minus negative x. What's going to go on the right side? Well, remember, it's if we plug in the negative version of the number, then it's the negative of if we'd plugged in the positive version of the number. So it's negative of if we'd plugged in the positive version of the number. So plugging in the positive version of the number, that's just if we had the normal x going in. Negative x to the fifth plus 2x cubed minus x. All right. So negative x to the fifth. Well, what happens when we have negative x to the fifth? What happens to that negative? Negative, negative, cancel. Negative, cancel. Negative. That fifth one, because it's odd, gets left over. So we've got negative, and we can just pull that negative out. It's the same thing as negative x to the fifth. Plus 2, once again, odd. Negative, cancel. Left with one more negative. Total of 3 negatives, so we're left with a negative. So we get 2 negative x cubed. Minus, we can pull that negative out as well, negative x equals, let's distribute this negative, so we get distribute cancellation, negative shows up here, cancel, so we get positive x to the fifth minus 2x cubed plus x. So let's finish up this left side, do cancellations over here as well, positive, this stays negative, positive, so we get x to the fifth minus 2x cubed plus x equals the exact same thing over here on the right side. Checks out. Yes, it is odd. Great. Finally, let's show that x plus 2 is neither. So to be neither, we have to fail at being this and fail at being this. So to be neither, it needs to fail being odd and being even. So it needs to fail even and odd. So fail, even, and odd. So let's just try plugging in a number. Let's try plugging in, say, -2. So if we look at x equals -2, then that would get us -2 plus 2, which equals 0. Now what if we plugged in the flip of -2? We plugged in +2. X equals +2. We plug that into x plus 2, and we'll get 2 plus 2, which equals 4. Now notice, 0 is not equal to 4. We just failed being even up here because the negative number and the positive version of that number don't produce the same output. Plug in -2, you get 0. Plug in +2, you get 4. Totally different things. So we just failed to be even. Great. Next, we want to show that it's not odd. So odd was the property that if we plug in the negative, it's going to be equal to the negative of the positive one. So 0 is not equal to -4 either, right? If we plug in -2, we get 0. If we plug in +2, it turns out that that's not -0, just 0. It turns out that's 4. So we fail to be odd as well, because it isn't the case that if we plug in opposite positive negative numbers, we don't get opposite positive negative results, because 0 is not the opposite of -4. It is just the opposite of 0, so it fails there. So it checks out. That one is neither. Great. All right, Cool. So we just learned a whole bunch of different properties, and they'll each come up in different places at different times. So just remember these, sort of keep them in the back of your mind. If you ever need a reminder, come back to this lesson, just refresh what that one meant, because they'll show up sort of in random places, but they're all really useful, and we'll see them a lot more as we start getting into calculus. Once you actually get to calculus, this stuff, especially the stuff at the beginning of this where we talked about increasing, decreasing, relative maximums, minimums, that stuff's going to become so important. You're going to understand why we're talking about so much right now in this course. All right. Hope you understood everything. Hope you enjoyed it, and we'll see you at educator.com later. Bye.